All right, so I'm going to start by restating a theorem I mentioned last time, and I will prove it, namely a characterization in terms of almost analytic extensions, for example, of C-infinity wavefront set, and analytic extension for real analytic wavefront set. So this is theorem 7. So let U be continuous near a fixed point x naught in Rm, and you take a direction, a non-zero direction always in Rm without 0, and so then let me say the following are equivalent. Then the following two properties are equivalent for U. One, the statement that x naught, C naught is not in the C-infinity wavefront set of U. And two, that there exists a neighborhood V of x naught, a finite number of acute cones, gamma j, 1j less than or equal to capital N. This gamma j has the property that the inner product with C naught is less than 0 for all j. And almost analytic functions, functions, u1 of xy up to u sub n of xy, such that the function u of x is the boundary value of these functions. And so it's uj x0, j1 to n, near x naught. Okay, so if you say basically on this open set V, after contracting V around x naught, if necessary. Okay. All right. So the proof. Let's see. One direction, this direction. Okay. So suppose x naught, C naught is not in the wavefront set of U. Then by definition, okay, now here, look, we are looking at U near the point x naught, so you can, by multiplying U by a smooth cutoff function, which is identically 1 near x naught, you may assume is of compact support, okay? So may I assume that U has compact support. So now, remember the definition of the wavefront set. So what does it mean that this direction is not in the wavefront set? Well, it means that there exists a cone. Let me call the cone C1 this time. A cone, okay, a cone containing this vector C1, such that the Fourier transform decays rapidly in this cone. Okay. Okay. So that's where this microlocal concept comes in. So it may not decay in all directions, but it decays in this fixed cone around C naught. Okay. So here is C naught, and you have this fixed cone C1 where the decay is. Now let me decompose then Rm as a union, a disjoint union of cones starting with 1, and then I may need, say, n of them, such that these cones are essentially disjoint. Essentially disjoint, maybe I shouldn't say disjoint, essentially disjoint in the sense that, say, their boundary may intersect, but so the measure of the closure of Cj, Ck is 0 whenever j is different from k. Okay, that's no problem. All you have to do is, so you have C1. Okay, remember a cone is determined by its intersection with the sphere. You have C1 and then just decompose the sphere, okay? So you have this number. And then now, since you see C naught is in the interior of C1, so therefore it's not in Cj for all j bigger than or equal to 2. And therefore, you can find cones. There exist acute cones, gamma 2 up to gamma sub n, such that C naught dot product this gamma j is negative, but the Cj, the Cj were like this, dot gamma j are positive for all j bigger than or equal to 2. Okay, this is easy. If need be, make the Cj smaller. Okay, okay. So now look at this condition. Now you see. So if say fix. I'm going to do something that I did yesterday. Namely, fix, say, one vector v naught in Cj, and maybe not call it v in Cj, y, say, in gamma j. Okay, or okay, v naught, y naught in gamma j. So for j bigger than, for some j bigger than or equal to 2. Now the condition that the dot product is positive. So if the dot product is positive for these two, say some number c positive, then you see there is a conic neighborhood of v naught and a conic neighborhood of y naught, so that the dot product of any two vectors from these two will be bigger than or equal to c over 2 times norm of v, norm of y, right? We've seen that yesterday, okay? So then by shrinking, if necessary, shrinking gamma j and Cj, may assume, in fact, that v dot y is bigger than or equal to c over 2 norm of v, norm of y for all vy in Cj cross gamma j. And there are a finite number of them, so there is a fixed number here, okay? That does that. Okay, so C naught dot gamma j is negative, but Cj dot gamma j have this property. Okay, now I'm going to define the following thing. First of all, u of x, what is u of x by the Fourier inversion formula? U of x is the sum of Eix dot c, u of x, the Fourier transform of u dc over Cj, j 1 up to n, because the union of the Cj, that the Cj's are essentially disjoint. It's only the boundaries that intersect, you know, and those are of measure 0, so they don't matter in the integral, right? So u of x is that. So I call each of these integrals the functions uj of x. So uj of x means this. Now I'm going to show that each uj of x extends, has an almost analytic extension in certain wedges. Okay, wedges defined by this cons gamma j. So let us start with so let j be bigger than or equal to 2 first. Okay, so I look at uj of x. It's the integral over Cj Eix dot c, the Fourier transform of j dc. Now in this integral, I'm going to complexify this, but the y I take it in gamma j. Remember now, gamma j dot Cj is positive. Okay, so for y in gamma j, if I look at I of x plus iy dot c, the real part of this is minus y dot c, and so if we put minus there, so this is less than or equal to minus c over 2 norm of y norm of c. So you see, so for y in gamma j, this integral will make sense. Okay? U is of compact support, remember. This, not U. Yeah. I'm giving this is I'm defining U here. So this is U hat of C. Okay, sorry. This is U hat of C. U is of compact support, so its Fourier transform grows at most polynomially, okay? And therefore, but you see for Y in gamma J, this gives you an exponential decay. So in fact, you see Uj of x plus Iy is defined. And so in fact, it is holomorphic. Where is it holomorphic? On all of Rn plus I gamma J on this code. Okay? It's holomorphic. Because you complexify, it's well defined. Is that right? The integral is well defined. Okay? So it's not just an almost analytic extension. In fact, it is an analytic. It has an analytic extension. This is for j bigger than or equal to 2. So next I have to look at u1 of x. Well, look at u1 of x. What is u1 of x? It is the integral over c1 eix dot c u hat of c dc. But here, you see, so far I have not used the hypothesis. You see, the hypothesis was x naught c naught is not in the wavefront set, which meant this. So on the con c1, this decays rapidly. If it decays rapidly, then this is in fact a smooth function of x on all of Rn, in fact, right? You can differentiate under the integral side. You get powers of c, but this is decaying rapidly, okay? So this is C infinity on Rn. Okay? So, and yesterday I proved that a smooth function on Rn has an almost analytic extension everywhere, in fact, not just in a wedge, in a particular wedge, okay? So this side is done then. Okay, I have written u of x as a sum of functions with almost analytic extensions in certain wedges, okay? You see, this is nice, you see. The definition of the wavefront set is not quite intuitive, but this is a much more intuitive description. Okay? So next, let me prove the converse direction. So suppose u is a boundary value of functions which are almost analytic. Each of them are almost analytic in certain wedges, namely in wedges where the gamma j, the directions, dot c naught is negative. I want to prove that x naught c naught is not in the wavefront set. That I have to look at u hat of c. Okay? Well, remember the proof of use the same ideas as in the proof of theorem 6. Remember yesterday where I took this cylinder that I called D? And what was D there? D was, you had a base, say B maybe here, was the set x plus t, it, or x plus t, y naught. And where I showed you what deformation of contour means in the C infinity case, remember, where I used the Stokes theorem and so on, use that proof, okay? Where you take y naught, okay? So you look at each uj, okay? So you want to prove that x naught c naught is not in the wavefront set, okay? Well, it's enough to prove that x naught c naught is not in the wavefront set of the uj. So for each uj, when you take the Fourier transform of uj, you will be able to deform a contour in this new sense by using the fact that the uj are almost analytic, okay? And then exactly the same proof that I showed you yesterday, okay, will work, okay? And so the theorem, so that's how the theorem is proved. Now let me give you the analytic analog of this, which I call theorem 8. Any question, by the way, so far? Okay, so the analytic, so let u be continuous near x naught, so this is theorem 8. Okay, I take a zero direction. The following are equivalent. This is not in the analytic wavefront set. There is a neighborhood of cones, blah, blah. But this time, and analytic or holomorphic, okay, and holomorphic functions. This is really very nice. You see. You see how parallel the theory is. You see for analytic wavefront set and C-infinity wavefront set. You see this characterization. You see, in the definition we use the usual Fourier transform for C-infinity wavefront set and the FBI for the analytic wavefront. But in this characterization, we are using the same kind of language. Okay? Now, the only difference is that almost analytic replaces analytic. Okay? Now, and the nice thing is the proof will be the same. The proof for one direction, the one I showed you, will be the same, where instead of the usual Fourier transform, you have to use the FBI transform, because that's what the hypothesis tells you. Okay? Use the FBI transform. And, well, what did the proof here involve? Well, we use the fact that you have the Fourier inversion formula. Well, we have proved an inversion formula using the FBI. Okay? And then you decompose just like this and you proceed like this. The converse will also be the same. Okay? The same idea. Details in our book. Okay? So, proof. Okay? Use the same ideas except the FBI replaces the usual Fourier transform. Okay? All right.
In the first result, if it's just continuous, right? In the first result,
yeah.
if it's just if was assumed to be only continuous, right?
Yeah, it could be a distribution.
Yes.
Yeah, it could be a distribution. It's true. Okay.
Measurable function.
You see, you have to get bounded, for example. Locally integrable. Something which you can define as a distribution will be fine. Okay. Yeah.
Here usually are holomorphic on V cross common cone, right? Here usually are holomorphic in where on V cross.
Holomorphic. Well. On V plus, good question. Not on the whole direction, but a truncated thing, which means you take, so gamma j delta means you take your gamma j and then take the sphere of radius delta and then in this, okay, in short term, okay? Yeah. All right, so now I'm going to show you a nice application to PDEs, to first order complex vector fields. For example, there are many people are interested in, including some in the audience, so-called CR vector fields, Cauchy-Riemann vector fields, okay? So I'm going to show you applications to regularities of solutions of those, okay? So remember yesterday I mentioned the following theorem. Namely, if you take a differential operator of any order, and if Pu is 0 or a smooth function, but let's say Pu equal to 0, then the wavefront set of U is contained in the characteristic set of P, right? The zeros of the principal parts, right? I stated this, okay? This I'm not going to prove, but we are going to prove it for the first order case, when P is first order. And this, if P has smooth coefficients, and if P has real analytic coefficients, the analogous theorem is true. And if P has Gevrey coefficients, it's true that there is something called the S wavefront set. That's also true, okay? All right, so the Gevrey stuff I have not touched at all. How you characterize Gevrey spaces locally, microlocally, using FBI transform, I didn't touch, but that's all contained in one of the references you get from Dr. Florian. There is a paper I wrote with a former student of mine, and you'll find the Gevrey details there, okay? So I'm not going to talk about it here. All right, so what I'm going to show you is this, the proof for this theorem for first order PDEs, okay? Now, traditionally, this kind of result is proved using what are called pseudo differential operators. But first, let me motivate for you why one expects a result like this. Why is this true? Or even more generally, if you have f here and here, say f is infinity, or in this case, f is real analytic. Why this is true? Roughly the following is this. So idea. Suppose P actually was a constant coefficient operator. Okay, say constant coefficient operator, and you have this. You take the Fourier transform of both sides. Then you get P of C, U hat of C, F hat of C. The reason I took constant coefficient is because taking the Fourier transform is easy. Okay? And then this tells you that basically U hat of C, at least where P is different from 0, is F hat of C over P of C. Right? Now, this decays, say, rapidly in this infinity case because F is infinity. So for this whole thing to decay rapidly and thus imply that U is also smooth, you have to have a control over 1 over P of C. So the growth of 1 over P of C has to be overpowered. It has to be dominated by the decay of F hat of C. But P of C is a polynomial, right? So P of C is a polynomial. It's bounded above by a polynomial growth, but that doesn't help me. I want to bound 1 over P of C. So I have to make sure that P of C is bigger than something. And that is what is true in the elliptic directions. When you are away from the characteristic set, that's exactly what happens, and that's why U hat will decay. Okay? This really is the basic idea. Okay? This really is the crux of the idea. Now, if P has a variable coefficient, I cannot take a Fourier transform like this, but there is a theory of what are called pseudo differential operators, which basically are inverses of differential operators that allow you to do this kind of thing. Okay, this kind of technical and so on, but the basic philosophy is this. Okay, that's why solutions of partial differential equation. On solutions of partial differential equations, you can use this idea of wavefront sets, microlocal analysis, to understand their regularity. Okay? Now, for the first order case, I'm going to prove it without using pseudo differential operators, using just the machinery we studied in this mini course. Okay? So this is the theorem I'm heading to. So L, I will call it, is a first order vector field. Okay? It could come from the CR vector field, any vector field. I have LU equal to 0, so U is a solution, okay? And I want to prove that the wavefront set of U is contained in the characteristic set of L. And here it could be analytic wavefront set, Gevrey wavefront set. So I'll prove the smooth and analytic case. Okay, is that clear? I'll prove the smooth and analytic case for you. That I hope I'll be done by the end of the second lecture. Okay, and then at the end of the second lecture, I'll try to pose a problem you can work on. Okay, using. All right. So here is the basic lemma now. Main lemma is the following. So lemma. So I'm taking L. So L is a first order vector field, which is non-degenerate, meaning at each point the vector field is not completely 0. Okay. You think about it. If L has coefficients that are 0 at a point, 0 times U equal to something, that's not going to tell you anything about you, right? You don't expect to get any. So that's a fair assumption. Okay, L is non-degenerate. In which case, you see, so L could be, for example, A1 of x d by dx1 plus A2 of x d by dx2. Say if I look at near the origin, either this coefficient is non-zero or this coefficient is non-zero. Say this coefficient is non-zero, so near the origin I can divide by A2, and I can assume that L starts with d by dx2 plus blah blah. Okay, it's not going to affect things. Okay, so in that spirit, then I write L as d by dt plus aj of xt d by dxj. Okay, so I take a vector field like here, and for now let me assume that aj c1. Okay. The theorem I'm going to prove here is for LC infinity, okay, for LC infinity, not LC1, okay? But even for C1, sometimes this will be true, under some additional assumption. And the reason I'm going to do this for you is because this has applications to regularity of solutions of fully nonlinear equations. Okay? Fully nonlinear equations. When you study regularity of fully nonlinear equations like this, you know, nonlinear equation, usually the way you tackle it is by trying to use your knowledge on linear PDEs. So you have to somehow linearize the equation. When you linearize, you have to differentiate, blah, blah. And then unavoidably, you will have to deal with vector fields whose coefficients are not smooth, which may be only like C1, okay? So that's why I'm proving this for you, okay? I'm going to state this for you, yes?
So this L, I mean, is this locally written as like this or this is global?
No, locally, because the questions we are going to look at is local.
Yes.
So if LU equals 0, is U smooth? Well, smoothness is a local question, okay? So I focus near a point, so L is written like this locally. You see, remember I said you divide by this because this is non-zero, that's local, okay? So yeah, this is local, good question. Okay, let L be like that, and I'm going to make some assumptions on, so this is a C1 vector field, and I take a function, assume f, which is a C1 function, so say on an open set U, C1 in U closure, and I take a solution. Well, I'm going to relax it. I'm going to take what is called an approximate solution. It's like an almost analytic extension, okay? So remember, almost analytic extension means d bar of f was flat at the origin, meaning this grew like this, right, for all k? Well, instead of the Cauchy-Riemann operators, if I replace this by an L, I can still talk about almost approximate solutions, okay, a solution where LF, a function where LF is flat at t equal to 0, to infinite order, okay? So f is behaving like a solution, okay? All right. Now, suppose, this is a key assumption, suppose you have m functions. So these are m functions on U closure, such that when I write, such that if I write zj of xt to be x sub j plus t times j, okay, xt, okay, for j 1 up to m, then the Zj are also approximate solutions. Okay, suppose, I'll tell you when these conditions are satisfied. I'll show you in a minute that if the Aj were smooth, to infinity, then in fact, you always have these kinds of functions. You always have this, okay? Okay, now an assumption about being not in the characteristic set of L. Okay, I want to study the regularity of this F, okay? LF is, for example, it could be 0, but this is even more general. This is saying LF doesn't even have to be 0, okay? Okay, so fix the point in Rm and the direction C naught in Rm also. Okay. Now here you see we are in Rm plus 1. You see here is x in Rm. And this is t. So we are in Rm plus 1. This U is an open set like this. So this is okay. But here is how I choose this. So here is a basic assumption. Assume that you have these coefficients, a1 up to am. They give me a vector a. These are complex valued, by the way. Okay? These are complex valued. So I take the imaginary part of that vector. Assume that at x naught, say 0, comma 0, inner product C naught. Assume that this is positive. we'll see that this basically means that you are not, C naught is not in the characteristic set of this vector field L. Then the conclusion is that X naught, C naught is not in the wavefront set of f of this function of x. Okay? So I'm not getting information on the wavefront set of f itself. F is a function of the x and t. But I get information on the wavefront set of f on the x-axis. And that is basically, you see, because, so I do get a regularity result, but you see, f is not a solution. It's an approximate solution. What I'm saying is, even for an approximate solution, I do get a regularity result. Okay? Moreover, L is only assumed to be C1. So even for L C1 and f an approximate solution, I get this. Under this assumption. This assumption may not be true for a C1 vector field, any C1 vector field. Okay? Okay? It turns out to be true if L is something that is associated to some nonlinear equations. That's why these conditions are there. Okay? All right. So this is the important lemma. From this, we will easily get this theorem. I'll show you that the wavefront set of U is contained in the characteristic set of L. Okay? Is that clear?
The Zj are
xj plus t times phi j of xt. Yeah. T times phi j. Yeah. Okay. Let me make a remark about when such Zj exists. Remark. If the Aj were C infinity, the Zj exists. The Zk exists. Let me tell you why. You see, what are the Zj? The Zj are functions which at t equal to 0, they give you xj. And the other requirement is that the Zj are approximate solutions. They are the analogs of almost analytic extensions. Okay? Well, remember how I showed you that given any function f of x, smooth, then it has an almost analytic extension. Okay? There is a function capital F, which is d bar flats. Okay? How did we do that? We saw that this condition forced upon you what the y derivatives of capital F had to be along the x-axis, and then you used Borel's lemma. Likewise, this condition will force what the Taylor series of Zj has to be, and you can determine the Zj. Okay? Okay? But that is when L is infinity, has infinite coefficients. Because in this approach, you have to differentiate the coefficients of L, okay, as many times as you want. Okay, is that clear? So, so in particular, if the Aj are infinity, then this hypothesis holds, and so therefore this result holds. Okay, let me prove this now. I hope I'll finish proving this now. Otherwise, I'll finish the proof at the end of the next lecture. So I'll go carefully through the proof, okay? I'll give you all the details for the proof, because this is a nice result, and you learn many things from the way this proof is, from the way this is proved. When I say you learn many things, you learn techniques that you can use in other problems, involving regularity. Okay, so first of all, let me show you, okay, so proof. So without loss of generality, you can assume, of course, that the point x naught is 0. Okay, that's not a problem. Okay, now I'm going to define vector fields. Let mj be bjl xt. So vector fields written only in terms of x, no d by dt. Okay, so these are m vector fields, little m, such that they have the following property. So you have these functions. Okay, you have these functions. So these vector fields have the property that mj applied to zk is a chronicle delta jk. That is 1 when j equals k, 0 otherwise. It's easy to show that these things exist. I'll show you. But what are these supposed to be? Let's take in the simplest example, you see, in the simplest situation, if L were just d by dt, if these coefficients were all 0, okay? So if L were d by dt, this, then you see, in that case, you see, the phase could be 0 here, you see, and then L, d by dt of the xj is 0, right? So the zj would be xt, xj. Okay, then the zj will simply be this coordinate functions xj, and in that case, what vector field satisfies this? Can you tell me? And so the mk have to be what form? Huh? D by dxk, right? Okay. So that's what we are trying to do. The analogues of this d by dx. Okay, so this you see, if you think of the zj, you see, so you have the zj defines these one forms. You have m forms. Okay, you have these one forms. Okay, we are trying to kind of find what's called a dual basis, right? Dual basis. So dual basis. Okay, is what these mls are. Well, anyways. This condition, you see, you put the mj in here. This condition implies that, you see, the b's will have to satisfy the following. If in matrix form, b11, b1m, bm1, bmm, this matrix times the Jacobian of z with respect to x of the zj. So dz1, dx1, dzm, dx1, dz1, dxm, dzm, dxm, that this has to be the delta jk, which is the identity matrix. Okay, that's what we. Okay, so that's what this is. This condition is equivalent to this. The bj are this. Okay, so these are the unknown. Now, this is an invertible matrix near the origin, because you see, this matrix, you see the zj, if you look at the Jacobian with respect to x, at the origin, at t equal to 0, the zj are the xj, so you get the identity matrix. Okay? This is the identity matrix, equals identity at 0, 0. Okay? At x equal to 0, t equal to 0. And therefore, by continuity, it's invertible near the origin, and therefore this will be the inverse of this from this equation. So B exists, okay? And the mj exists. Is that clear? So this is invertible near 0, 0, which is where I am working. I am assuming x naught is 0. And so therefore this exists as a smooth function. These are smooth functions, and therefore the mj exists. The mj exists. Now next I'm going to look at the key properties of the mj. First of all, claim that the mj are linearly independent. J are linearly independent at each point. Okay? So suppose you have a sum al, ml. Okay? And these are functions. Al of xt, ml equal to 0. I want to prove that the al are 0. Okay? Apply, so this is a vector field, okay? So apply the form, say dzk, to this vector field. Well, since this sum is 0, then this is 0. On the other hand, what does applying differential of a function to a vector field mean? It means you take the vector field and apply it to the function, right? That's the definition of the differential, right, of a function. So this is 0. But the MLs, remember, they are the dual basis. So the ml of zk is non-zero only when L is k, in which case it becomes 1, and so this gives you A sub k at each point. So we have shown AK is 0, and that therefore the MJ are linearly independent. Is that clear? Next, let me show you that the Lie brackets between any two of them are 0. Okay? 2. Two ML MI is 0 for all Li. Well, to prove this, well, this is a vector field. Any vector field can now be written using the Mi and d by and L. L has d by dt. The Mi contain basically any d by dxi can be written in terms of the Mi. You already see it at the origin. At the origin, you see this was the identity, which basically tells you at the origin, Mj is d by dxj. Okay? Mj is d by dxj. So this is a vector field, so I can write it as Aj Mj as a linear combination of this plus little b L, or just d by dt, b d by dt. Okay, now apply both sides to the form, apply to the form dt or to the function t. These are vector fields which are only d by dx's. There is no d by dt. And therefore, the bracket has only d by dx's, so when you apply to t, you get 0. On the right, this gives you 0, this gives you b. So b has to be 0, so this has to be a linear combination of this. Okay? So the bracket, in any case, has to be only a linear combination of the Mj. Okay, next, apply both sides to say, the differential of zk, meaning apply both sides to the function zk. Here, you'll get only ak, and on the left, you see, when you apply ml of mi of zk, for example, well, mi of zk is 1 or 0. In any case, since you're applying ml to it, you will get 0. Okay, and so therefore, the bracket is going to be 0. And so this tells you that the brackets are 0. Okay? These vector fields commute. And finally, you see, so I have this basis of vector fields, the Mi, the L. The reason I'm studying them is, you see, later when I try to estimate the wavefront set of a solution, I'm going to do deformation of contour again. Okay? I'm going to deformation of contour. But the forms that I use, when I integrate, they will not be the usual forms, dx1, dx2, dx3. No. I want to use these forms dzj, these vector fields ml, and a. That's how I'm going to because those are the ones that are tailored to the problem. Okay? So you'll see this. You'll see this in a few minutes. So finally, if I take any of this and this, I leave it as an exercise for you. You can show that this is a linear combination of the Mj only. And so this is CJS. So use the same idea. Okay? Yes, where S, CJS, in fact, are flat at the origin. Okay? So these are the properties. Now let me show you, now here comes one of the key ideas. How to write a form using this kind of vector fields and so on. Okay? So any form, so if h of xt is a function, is C1 say, the differential of h, well, it can be written in terms of a basis of one forms, right, in xt space. And the basis of one forms we have seen here is, for example, the dzk, k1 up to m, and then there is the dt. Okay? So b times dt. Differential of zk and b times dt. Now, The reason this is true, the reason these guys and this form a basis is because at the origin, remember, the dzk are like dxk, okay? So now I have to write what these coefficients are in terms of h. To do that, you apply this equation to the following basis of vector fields. Apply this to this vector fields, m1 up to mm, L. That's really, when you apply to mj, look at what happens. Apply to one of the mj's. This side, well, this side will be mj applied to this means mj of h. This side, mj, remember, is only differentiation in x, so it kills this. mj over here acts only when k equals j, and in that case it gives you aj. So this is nice, you see? So when the differential of h is expressed using the differential of zk and dt, then the ak are exactly mk of h. All right. The b, how about to recover the b? Now I apply L to both sides to get L. So apply to L. That's what you get. On the left side, you get LH, L of h. On the right-hand side, well, I get L of zk, the sum, ak, but ak is, now we know what that is, mk of h, L of zk, and remember L of zk are almost zero. They are, the zk are approximate solutions, okay? They're flats at t equal to 0, okay? Okay, I get that. Plus, when L acts on this, L is d by dt plus differentiation in x, so only d by dt matters. So L of this is just b. So therefore, you see, I know the ak is mk of h. The b is a little complicated. B is this minus this, okay? So b is L of h minus k 1 up to m, mk of h, L of zk. Let me remark, if the zk were actually solutions, which is what happens if you are dealing with what are called CR structures, blah, blah, okay? Or if the L, if the vector field L were real analytic, the zk will not only be approximate, you can get them to be solutions. In that case, you see, B becomes very simple. So B becomes L of h, this becomes mk of h, so this whole description will be nicer, okay? Now, this is how I will express a form in the deformation, to use Stokes' theorem, okay? So now, instead of a function, if I take an M form, differential of G, for example, dz1 wedge dzm. Well, this is differential of G wedge dz1 wedge dzm. I told you what the differential of a function is using this. This part will not matter since it will kill this. So only this part comes in. And B is this. And so what I get is, what is that? I get L of G minus mk of G, L of zk, okay, dt, wedge this, which I will call dz simply. Okay? This is what I'll use. I'll go over it when we start basically integrating by part or using deformation technique. Okay? So the time is essentially up. I mean, I have 5 minutes, which I want to leave for questions. Thank you.